is the Rio Grande. Like many streams throughout the country, it flows in an alluvial channel. This means it flows through a valley filled with material deposited by the stream itself, sand. Here the bed of the Rio Grande is sand. As you can see, sand channel streams can carry great amounts of sediment. It is 3,000 cubic feet per second, but not all of this discharge is water. At times in the Rio Grande, what is reported as water is 10% weight of sediment. However, some tributaries to the Rio Grande carry as much as 60% by weight of sediment. In sand channel streams, the relation between depth, discharge, sediment transport, and other variables is very complex. All are interrelated. The elevation and configuration of the stream bottom may be changed by the flow. The stream bottom may be quite flat at one discharge. While at a smaller discharge and shear stress, the bottom may be covered by large dunes. We shall explore these problems and try to explain some of the mechanics of flow in alluvial channels. However, before we can discuss these problems, we will review a few concepts pertaining to open channel flow in alluvial channels. This is the Bernoulli energy equation. It states that the energy in a system remains constant since energy can be neither created nor destroyed. The first two terms in the equation equal the static head. It represents the potential energy in a system. In open channel flow, it is the elevation of the water's surface. The third term is the velocity head. It represents the kinetic energy in the system. The sum of these terms determines a point on the energy grade line. If there's a steady uniform flow, velocity does not change with time nor distance, and the slope of the energy grade line will be parallel to the water's surface. We know steady uniform flow does not exist in nature, but the assumption often is a good enough approximation. The friction head loss, H sub F, by finding the drop in the energy grade line between 2 points. If we add the depth of flow at a point to the velocity head, we have what is called the specific energy H. This is the specific energy diagram. Specific energy is plotted against depth with discharge held constant. For a given specific energy, two depths of flow can occur. At one point, specific energy is a minimum and only one depth occurs. The depth at this point is the critical depth, and the velocity corresponding to this depth is the critical velocity. With this condition, the velocity divided by the square root of the depth times the acceleration of gravity, called the Froude number, is equal to 1. For Froude numbers less than 1, the velocity is less than critical, and the depth is greater than critical. This is tranquil flow. For Froude numbers greater than 1, the velocity is greater than critical, and depth is less than critical. This condition is rapid flow. tranquil flow, surface waves are out of phase with the bed configuration. For rapid flow, surface waves are in phase with bed configuration. Quite often, when flow is rapid and the slope gets flatter, or an obstruction is across the path of the flow, a rapid change in elevation from the rapid flow depth to the alternate tranquil flow depth will occur. This is the hydraulic jump. Consider a free body diagram of a section of the river. Fluid shear at the boundary per unit area is equal to the specific weight of water times the depth times the slope of the energy grade line. Fluid shear is the driving force for the movement of the sediment and change in bed configuration. The characteristics of bed materials such as size, fall velocity, and range of sizes are important in determining resistance to flow and sediment transport. Consider fall velocity. It is the terminal velocity of an isolated grain falling under its own weight, resisted by fluid drag. In the same fluid, the smaller the particle, the smaller its fall velocity. The more viscous the fluid, the smaller the fall velocity. Particles the same size will have different fall velocities if the fluid viscosities are different. A large particle in cold or heavy clay-laden water may have a fall velocity equivalent to that of a smaller particle in warm or clear water. Knowledge to date indicates that if fall velocities are the same, the particles react similarly to fluid forces, even though their physical sizes are different. Because fall velocity is important, the visual accumulation tube is used to determine the physical size of bed material particles. In analyzing a sediment sample in the VA tube, the engineer determines the water temperature. Places the mixing rod in the mixing chamber and closes the valve to the sedimentation column. He transfers the sample to the mixing chamber. The sample is washed and mixed with the plunger. Immediately after mixing, the valve is opened, automatically starting the recorder drum. As soon as the first particle reaches the bottom, the accumulation is followed upward by turning a hand crank to keep a crosshair on the upper surface of the accumulation. A pen moving with the eyepiece draws a time accumulation line on the VA tube chart. The sand particles accumulate in the column according to their fall velocity. Diameters determined by the VA tube are given in terms of equivalent quartz spheres with the same fall velocity as the particles in water at 24 degrees centigrade. This is the accumulation curve that was traced for this sample. From this chart, the percent finer than any given size in a sample and its graduation can be determined. It takes many analyses of many samples to obtain a realistic indication of the size composition of the alluvial bed. Although we are familiar with the meaning of the term water discharge, the many terms used for sediment discharge or load may be confusing. First, the sediment discharge is classified according to source. There is bed material load, which, as the term implies, is the sediment load derived from the bed. There is a fine sediment load, which is the sediment load that originates from a source other than the bed. Fine sediment load is not found in appreciable quantities in the bed. Second, sediment load is differentiated by a mode of transport. There is a contact load, often called bed load, which moves in approximate contact with the bed. And there is suspended load, which is the material that is moving supported by fluid turbulence. Bed material load is carried by both modes of transport. However, fine sediment moves mainly by suspension. Suspended sediment load may be measured with DH-48 suspended sediment samplers. Total sediment load is the total amount of sediment moving past a given cross-section. It is the fine sediment load plus the bed material load, or the suspended load, plus the contact load. We're now ready to talk about alluvial streams. The shape of the bed of a sand channel stream is formed by the flow. There are several bed forms that can exist. These bed forms are a function of the characteristics of the flow, fluid, and bed material. In a natural stream where the energy slope is normally constant, a change in depth may change the bed form. In the laboratory flume, holding depth of flow constant and increasing the energy slope progressively, the following bed forms will occur. Plain bed without movement of sediment, ripples, ripples on dunes, dunes, transition zone, where the bed roughness can be anything from dunes to a plain bed with movement of sediment, standing sand waves, anti-dunes, and violent anti-dunes. The first three bed forms are grouped together insofar as roughness, form, and sediment transport are concerned. They have been classified into the lower flow regime. In this regime of flow, the water and sand waves are out of phase, just as in tranquil flow with a rigid boundary. Sediment transport is relatively small, 1 to 1,500 parts per million, and resistance to flow is large. Manning-Ann will vary from 0.018 to 0.040, and Chessie-C from 44 to 60. The last four bed forms are also grouped together insofar as roughness, form, and sediment transport are concerned. They have been classified into the upper flow regime. In this flow regime, the water and sand waves are in phase, just as for rapid flow with a rigid boundary. Sediment transport is large, 1,500 to 60,000 parts per million or more, and resistance to flow is small. Manning-Ann will vary from 0.012 to 0.018, and Chessie-C from 50 to 120. Resistance to flow and sediment transport varies between wide limits because the form of bed roughness, as well as resistance to flow and sediment transport, is related to the fluid, flow, bed material, channel characteristics. Now, let us observe these flow regimes and bed forms in the laboratory flumes at Colorado State University. With small boundary shear, the bed is relatively plain and there is no movement of sediment. The resistance to flow is the result of grain roughness. Manning-Ann ranges from 0.012 to 0.017, depending on the size of the bed material. As the shear stress increases, sediment begins to move. This shear, necessary to begin movement, is called the critical or threshold shear. Once the sediment begins to move, ripples will rapidly develop on the bed. These time-lapse movies show the development of ripples. Although the formation of the ripples can be illustrated, no physical explanation of their development is possible at this time. Resistance to flow increases considerably as ripples fully develop. Manning N is now 0.025 and Chesney C is about 60, whereas with the plain bed, Manning N was 0.014. Ripples are relatively small. They're about 0 to 2 inches high and measure 6 to 18 inches from crest to crest. The grid on the flume is 6 inches square. Ripple size is independent of the depth of flow. Almost all sediment movement is in contact with the bed. There is little or no suspended sediment load. Particles roll up over the crest and come to rest on the ripple face. In this way, ripples move downstream. The water surface is quite smooth, water clear, and ripples are approximately parallel to each other and tend to be perpendicular to the flow. The form of the ripples is similar for bed materials finer than about 0.7 millimeters. However, for coarse bed materials, ripples apparently do not form. Instead, we have long, low-amplitude dunes. These dunes are 2 to 3 inches in height and 2 to 3 feet long. As the shear increases by increasing slope or depth, dunes form. The resistance to flow may increase or decrease with a change from ripples to dunes depending on size of bed material and depth of flow. The dunes are much larger in amplitude and spacing than ripples. These dunes are in the 8-foot wide by 2-foot deep flume and are approximately 9 inches in height and 3 to 6 feet long. There are ripples on the backs of the dunes. At larger shear stresses, these ripples will be eliminated. Boils on the water surface are a good indication of dunes. These time-lapse pictures show the movement of the dunes. Note that it is the contact load that causes the dunes to move downstream. The grid on the window is 1 foot long and 1/2 foot high. The turbulence is much greater with dunes than with ripples. Some of the particles carried over the dunes are transported by suspension and deposited temporarily further downstream. The velocity of flow is relatively high close to the bed on the back of the dunes. A large separation zone with strong reverse flow is set up in the trough. reverse flow will move some of the bed material upstream in the trough. Resistance to flow for dunes as measured by Manning N ranges from 0.018 to 0.040, depending on the amplitude and length of the dunes. Resistance to flow with dunes results from grain roughness on the back of the dunes and form roughness downstream from the crest. The dune deposit is at the angle of the dune face, whereas the trough deposits are almost horizontal. The result is an easily distinguishable cross-bedding. The sand bed is much softer for dunes than any other bed form. This, plus the troughs, make it difficult to obtain accurate depth measurements. The softness and porous nature of the bed is apparent considering the settlement in the bed when the flume is jarred. Taking suspended sediment samples when the bed roughness is dunes requires special care to avoid dipping the nozzle into the bed. Dune height and spacing is related to the depth of flow and size of bed material. The finer the bed material, the longer the dune. Thus, resistance to flow is less for a dune bed of fine sand. In addition to the troughs, there are deeper holes downstream of the dune crests. These are the potholes noted when measuring in an alluvial stream. Dunes do not occur in parallel ridges in the 8-foot flume or in the field to the extent that ripples do, and the water can meander around the dune crests. This decreases the resistance to flow. In the small 2-foot wide flume, the bed form is two-dimensional. That is, the dunes are in parallel ridges in contrast to the dunes in the large flume or in the field. Consequently, resistance to flow for the same depth and sand size is greater in the small flume. As shear is increased, the transition from lower to upper flow regime occurs. The dunes become more elongated and, ultimately, at greater shear stress, wash out. As the dunes elongate, resistance to flow decreases. Chessie C is increased about 20%, and sediment transport doubles. Once again, as shear is increased, the bed form changes. The dunes disappear, and both the bed and water surface are relatively flat. This is the glassy, smooth surface often noted when the discharges are high on streams with fine sand bottoms. Sediment discharge is much greater with the plain bed than with dunes. The resistance to flow is smaller than for washed-out dunes. Manning N is 0.010 to 0.012, and the Chessie C is equal to about 120. Resistance to flow is even less for this case than for a plain bed without sediment movement. Some streams may not develop a plain bed. If the slope is steep enough or the sand coarse, standing waves may develop rather than a plain bed. These are the waves noted so often in the field. Despite the appearance of the water surface, there's very little large-scale turbulence. The surface waves have a greater amplitude than the sand waves, but the two wave trains are in phase. Streamlines are nearly parallel. Sediment load increases considerably because the movement is continuous. Most of the bed load moves as contact load. Resistance to flow with standing waves is almost the same as for a plain bed. That is, Manning N is around 0.012 and Chessie C is around 110. As shear is further increased, antidunes develop. Antidunes are quite similar to standing waves, except they move upstream and usually break. Bed material is eroded from the downstream side of the sand wave and deposited on the upstream face of the next wave downstream. Thus, although the bed material movement is downstream, the antidunes move upstream. The breaking wave occurs when the trough of the surface wave is lower than the crest of the adjacent sand wave. The breaking antidune is similar to the hydraulic jump. A portion of the energy of the flow is dissipated by the breaking waves. However, because the breaking wave occupies only a portion of the flume and time of flow, resistance to flow with antidunes is only slightly larger than with standing waves. Antidune activity increases with increasing slope and decreasing size of bed material. Consequently, the resistance to flow also increases. We mentioned earlier that changing the temperature of the flow by changing the fall velocity of the particle may change the form of bed roughness. Here, the water is cold, temperature of 10 degrees centigrade, and the bed is plain. As we warm the water, decreasing viscosity and increasing fall velocity of the sand, dunes form and resistance to flow increases. Increasing the concentration of fine materials such as clay in the water has the opposite effect of increasing temperature. That is, water viscosity increases and fall velocity decreases, and the bed form changes from dunes to plain bed. The maximum temperature is 40 degrees centigrade. By decreasing the temperature, the plain bed reappears. Now let us see how the experience gained in the laboratory can be applied to the field case. Here we are on the Rio Grande, near Bernalillo, New Mexico. The flow is 3,000 cubic feet per second, and the bed form is dunes. The slope is about 1 foot per 1,000 feet, and the average depth is about 3 feet. The suspended concentration is approximately 2,000 parts per million. Notice the boils. They are indicative of the dunes. The boils are over the troughs and potholes downstream from the crest of the dunes. The average height of the dunes is measured from the crest to the trough is about 2 feet, and their length is about 20 feet. The bed is very soft and often feels like quicksand. Boils and potholes signify that bed roughness is dunes. A field verification of Manning N give a value of 0.025 and a Chevy C of 63 for this site. This compares with the Manning N of 0.025 and the Chevy C of 64 for dunes in the same bed material in the laboratory flume. A very close agreement. In the field, dunes are the most common bed form in the lower flow regime. This is still the Rio Grande near Bernalillo, and the slope is still 1 foot per 1,000 feet. However, boundary shear has increased, and the bed form has changed from dunes to a combination of plain bed, standing waves, and anti-dunes. These are the sand and water waves often noted in the field. The resistance to flow is about the same as for a plain bed. The Manning N is 0.016, and the Chevy C is 125. As illustrated, more than one form of bed roughness may exist in a reach. Here we have standing waves, anti-dunes, and plain bed in the same reach. It is entirely feasible to have standing waves and anti-dunes in the middle of the stream, plain bed adjacent to the standing waves and anti-dunes, and dunes or ripples adjacent to the plain bed. In this situation, the resistance to flow is a function of the area of the total bed occupied by each bed form. height of the standing waves and antidunes are equal to the depth of the water. Here, the depth is about 3 feet, and the height of the wave about 3 feet. The distance between wave crests is about 18 feet. The length-to-height ratio is essentially the same as that measured in the laboratory flume. Despite the breaking and reforming of the antidunes, the roughness is not increased appreciably. The breaking of the antidunes causes a great deal of material to be thrown into suspension. The height of the standing waves and antidunes are equal to the depth of the water. Here, the depth is about 3 feet, and the height of the wave about 3 feet. The distance between wave crests is about 18 feet. The length-to-height ratio is essentially the same as that measured in the laboratory flume. Despite the breaking and reforming of the antidunes, the roughness is not increased appreciably. The breaking of the antidunes causes a great deal of material to be thrown into suspension. A sample taken of this flow showed a concentration of sediment of about 8,000 parts per million. The change in flow regime has a definite effect on the stage discharge and depth discharge relation. Here is a plot of the relation of velocity to hydraulic radius for the Rio Grande near Bernalillo, New Mexico. The left-hand curve is the average depth discharge relation for the lower flow regime when the bed was dunes. The right-hand curve represents an average relation for upper regime flows when the bed form was plain bed, standing waves, or antidunes. Between the two regimes of flow, there is a transition when the bed form may range from that typical of the lower flow regime to that typical of the upper flow regime. And the resistance and sediment transport are also in transition, ranging between conditions for the two flow regimes. A good description of the water surface appearance and the compaction and shape of the bed would aid in establishing the regime of flow and thus the water and sediment discharge rating of the stream. Every measurement of water and sediment discharge on a natural sand channel should include as good a description of the water surface as possible. A few minutes spent there during the measurement may save hours of work later when the measurement is interpreted.